Yeah. Okay, guys. So it's almost a time. So we can start now. So before we begin, let me give my introduction to you that my name is Vikas Kumar Mishra and from IIT Patna. I am doing PhD under the Dr. Devendra Yadav. My department is Metallurgical and Materials Engineering, and I found that this course is must and necessary for every metallurgist who is in the PhD, who is in the research, even for the BTech, they all should be aware about this. And so it's a very good opportunity for me to learn and to help others also to solve their doubts. So what is the aim of this particular doubt solving session is that in the video lecture you can see that there are the lecture is provided, the professor taught us many things. It's a very beautiful lecture. And the thing is that there is a limitation that one by one conversation we cannot have. There is only one sided conversation there. So if you face any doubt, any difficulty in that, you can do two things. One is that you can post it on our doubt solving forum, and also you can join these particular lectures and we can have a detailed discussion on that. This is the first thing, and second thing is that our aim is to make sure that you are able to solve your assignments on time and you don't face much of the difficulty. So to solve those, to make sure that you are able to solve the question easily, comparatively. So for that only, we are going to solve few similar type of questions, based on which we can solve the assignment question and also we can understand the concept more clearly. So let's start with this particular course and let's have a look on the list of the. Okay, yeah. So guys, can you please mute yourself? Okay. If you face, okay, if you face anything like if you want to interact with me, please feel free to unmute yourself and interact. And if you want to answer something, you can also post it in the chat also. Okay. So these are the list of the content that has been covered. So we started with the basic principle of the image formation. Like for the any microscope, not only optical microscope, for any microscope, how the image form, even for our the human eyes. So how this the image formation takes place, that we have discussed. Then we discussed the concept of the resolution, magnification, depth of field, and depth of focus. After that, we discussed the aberration in the microscope. What are the aberration? What are the limitations that can be imposed on the microscope? From where those are coming? So we discuss about the aberration part, okay, and then we discuss about the image formation in the optical microscope. Okay, then we had detailed information about the component which are present in the optical microscope, starting from the eyepiece to the stage to the luminance source and the objective lenses, which is very important. So with that, before I start the questions part, let me ask you that, do you have any doubt till now, whatever has been discussed in the class, in the lecture? If yes, please feel to discuss with me. If no, then we can start further. Okay, seems like there is no. You can always put your questions in the chat box. We will tackle it once we are free with the questions. And at the end of the doubt solving session also, I will ask you the same thing, like, do you have any doubt? Then please feel free to respond. So now let's start with the few questions, few basic questions. The first one is that the word microscope originate from the two Greek words, that is micro and scopian. What does these two words mean? What does they represent? So whether it's option A, B, C or D. So we have micro and we have scopian. What does it mean? What does the word micro means? And what is the word scopian means? So we know that micro means something which is small. And scopian mean is something which to see, to visualize. Right? So among this A, B, C and D, which one will be the correct answer? Please feel free to write in the chat box your opinion, what you think. If there is any conflict in that, then we'll try to solve them. So here we understood that the word microscopian. Yes, Krishna sir has wrote is right, that it's option A is the correct one, where it's a small and our scope is to see it, right? It's a miniature. Second option is sitting there. Miniature is okay. We can still consider it, but to magnify, no. Microscope does only mean that we want to see something small features or small objects, right? So option B is not correct. We are not here. This entire microscope word, it doesn't take consider about the magnification. The word large and to measure, no, it's not. None of the other. Okay. So the right answer is option. Very good, everyone. Okay, so Namrata has told that it's option B. So we got to know that why the option B is not correct one, because the scopian word, it means that it's a scope that is to see, to visualize. Okay, so with that we have solved the question number 1. If any doubt, let me know. If not, let's move to the next question, question number 2. All the questions are at the initial stage, they are quite easy, but as we keep on proceeding, the questions will keep on, the level will keep on increasing. Yeah. So question 2, which of the following microscope forms an image pixel by pixel? That is, let us say, after microscope, after you got an image, whether your microscope scanned it one by one, each pixel, and then generated the image. Or it can also be one way that this is your specimen and the beam has transmitted through it. Okay, and now gave you the projection. So here it's not this is not pixel to pixel. We are not scanning one by one. Okay, what we are doing? So here everything will be at a time, within a instant you will get. While here, if some microscope is using one by one, it's scanning a particular region, then going to another region like raster mode. So that is what is known as a pixel by pixel. So what do you think? Among optical TEM, SEM and human eye, which one, which among this is used is pixel by pixel? See, optical microscope, it's nothing but we can take an analogy from our eyes. So whenever you see something, whenever you are, let's say we are seeing each other, I'm seeing to the screen, I don't have to scan one by one, right? So the what will happen that my eye will produce the image instantly. While if you see for the SEM will, what will do, it will focus on particular region, it will scan it, then again it will go to the another region, it will scan, it will generate the information from it like it's a probe. It will keep on doing that, and so will we get the image. Whenever you do SEM, you might see that your image, the formation of the image take a lot of time. It scans from the top to the bottom, while whether you use SC or BSC, in both the cases you see this thing that it will rush from one to another. And this is the reason that SEM is pixel by pixel. So which of the following microscope form an image pixel by pixel? It is the SEM is the correct option. TM again, you can do it. It's work in the projection mode. So again, you will get the instantly information you will get. Human eye is also you will get. So for these three things, it work in the projection mode. So if I ask you one question that, let us say one problem is there in front of you, which keep on changing with respect to the time. Like let us say some reaction is happening, and you want to detect that some information, some in situ you want to do. Whether you should go with the SEM, which raster by pixel, or you should select this type of images, this type of microscopy, which will directly generate the image within an instant. What will be the right answer? Not SEM, right? Because the scanning will take a lot of time. In that particular time, it might be possible that our reaction, our system, the thing which we want to observe, it might have passed. So the right option will be the optical, TEM or human eye, depending upon the scale at which we want to observe those things. Okay, so with that, we have solved this question number 2. If there is any doubt, let me know. If not, let's move ahead to the question number 3. Now, the third question. What does the term microstructure property relation refer to? Microstructure and property, what does this refer to? Color of a microstructure define its cost. Mechanical property depending on the atomic weight, depend on the atomic weight. Material property are influenced by its internal structure. Macro scale geometry define atomic behavior. What do you think among A, B, C and D, which one is the right answer? That's the microstructure and property correlation. What this term refer to? So we know that the right answer will be option C, because yeah, Krishna Raj, perfectly right. Yeah, Sweta, that's good. That's great answer, right? So option C is the right answer, because we know that if my grain size of the specimen, let's say I have a material. In one case the grain size is this, in another case we have the finer grain size. So we know that the property of this particular structure A and B will be different. Let's say talk about the metals. So here the hardness in the B will be the higher compared to the A. The ductility of A will be higher than compared to the B. Right? So we know that the internal structure, the structure which we are talking about, they are going to affect the material properties. Right? So with that we can say the option C is the right answer. Great guys. Okay. Yeah. Any doubt in this question? Question number 3. Okay. Since there is none, let's move ahead to the question number 4. So right now we are solving the question based upon the discussion that has been made in the lecture number 1, where we discuss about the SEM, TEM, optical in a very broad perspective, like what their capabilities are. So for the SEM, what do you think? Pixel by pixel formation, depth perspective, projection, this or shadow formation. So we know that, yeah, the Rajiv, perfect. The right answer is option A. Along with that, we can also select one more answer here. For the first one, for the SEM, we can select the answer A. We can also select the answer B because we know that the depth in the SEM is quite high. The, the depth of field is very high. So the option B is also the right answer. Now let's go to the second one, TEM. For the TEM, can we go to the depth perspective? No, we know that what it gives it gives the entire information throughout the specimen. Prahlad, yeah. So the option C, perfectly. So the right answer is option C. So we can visualize the dislocation over here. Correct? Very good. Let's move ahead. Let's go to the third one. What about the optical microscope? C, sorry, D or E? Yeah, that's right. There's option D is the right answer. We are using the natural images, natural color in this particular because the what we are using is the optical in the optical microscope. We are using the visual light. Now let's go ahead. Question number 4, the projection image. The projection image is, yeah, Rajiv is telling that's option E is the right answer. That is perfect, right? So in the projection, we know that we are more or less we are generating the shadow, whatever the information that has been there, we are reflecting it on. Okay. Now the fifth one, the scanning image. The scanning image, we know that it's again option A, that pixel by pixel, right? So with that, we have solved this match the page. Yes, Namrata, that's right. That's option A is the right answer. Okay, if there is any doubt in this question, let me know. If not, let's move ahead to the next question. Now, this fifth question is a little bit lengthy. Okay, so let's try to wait one by one. Now, true or false, right? The first one, the magnifying glass can be considered as a microscope. Is it true? The magnifying glass, which we usually, like if you zoom it, if you put it over here, the glass word, if I put the magnifying glass just above the glass, this word itself, it will get enhanced. Yes, perfect. Yeah, yes, Prahlad, it's a true. Yeah, that's right. Human eye is a system that transforms object into an image. Is it? We are seeing a lot of object. Yeah, this is also true. Option C, the third one. The dislocation observed using SEM scanning electron microscope. No, right? It's a false. Yeah, very good, Krishnaraj. Yes, sir. Rajiv, yes, it's perfect. So we solve the third one also. Now, the transmission electron microscope uses light as the source of the illumination. So it's a false. Then what does it use? Yes, yes, Namrata and Rajiv. Yeah, it's a false. So what will be the right answer? Like, if it's not using the light, then what it is using? The word itself is the, yes, perfect, the electron, right? So it is using the electron gun, Namrata. Yeah, perfect. So now the last one, the image formation in the TEM and optical microscope follow the same basic principle. Is it? Yeah, it's true. The ray optics in the SEM, sorry, the ray optics in the TM and in the optical microscope, they both are same. So with that, we have solved this question number 5. If there is any doubt, please let me know. Seems like there is no. Let's move ahead to the next question. Okay, so this discussion has already been made in the class regarding this question. What type of image is formed when the object is placed between the focal length f and 2f from the lens. The question is stating that, let us say this is the lens, this is the focal length, f, f, 2f, and 2f. The object is placed somewhere in between f and 2f. So what is the right answer? So Krishna Raj is telling that the option A is the right one, that it will produce the real, inverted, and magnified. Yeah, that's true. So here, if we follow the optics, so what will happen? It should pass through the center, and the next thing is that it will bend. So we can see that the final image will be quite enhanced. It's large compared to the object, and this is the reason. So this is the reason where our optical will place our specimen in the optical microscope. One more thing, more the object is close toward the f, that's why I use the configuration in the microscope, Rajit. Yeah, that's right, perfect. One more thing is that if we move our object location from this place to here, the again the image will be even further enhanced. So this is also one of the reason that why we are selecting our object, our specimen, to be near to the f, to be the closer toward the lens. Okay, so the right answer is option A. Okay, any doubt in this question? Okay, since there is no, let's move to the question number 7. Again, similar type of questions, you can easily answer it. So what kind of image is formed when the object is placed within the focal length? Right. So right now, this question is asking that what will happen if you place your object somewhere over here? See, it will be virtual and erect. That's correct. It will be virtual and erect. Let's see the solution for this. This is f. This is 2f. So we are placing our object somewhere over here. So it will directly go here, and then again, if we are making it parallel, then it will pass through the focus, right? So we can see that they are diverging from each other. They are diverging. So what we have to do is we'll move them back. We'll get it somewhere over here. So we can say that this is our image, but it's on the left side. So it's a virtual and same height, like in the same direction the height is there. So it's reactive. So the right answer is option C. Very good, guys. Let's move ahead if there is no doubt. Yes. So now we have already discussed this in the question number 6, but let's try to answer it again. In a compound microscope, the image formed by the objective lens is, so we are talking about the objective lens, A, B, C, or D. So the right answer will be here. So it's same whatever we have answered till now in the 6th question. So in the objective lens again, the is A, right? Perfect. Real and inverted. So if we try to see through the lens, whatever we are, if I'm seeing the image, it will be display something like this, right? Something like this. So it is a real, but it's a inverted. Very good. The right answer is option A. Since we are talking about the optical microscope, let's have a look onto the optical microscope which I am having. Let me see whether I'll be able to focus it or not. Yeah. Yeah, it's nice. So can you even tell me that this optical microscope which I am having, here is the optical objective lens. Here is the eyepiece. Here is the stage where I will keep the specimen. So can anyone tell me, this optical microscope is a what is the configuration of this particular microscope? Is it inverted? Yes, it's inverted. Very good. Very good, Prahlad. Yeah. Yeah. Yes, Rajiv. So we are going to place our specimen on top of this, and these are the objective lenses, which we are going to see that these are the rotating one. This rotating one are the objective lenses. So let's try to remove one objective lens and see what and all things are written over here. So this is my objective lens, for which we talk about that it is going to produce the real and inverted image. So this is the point. This part is going to focus onto our object, and from here it is going to reflect it, and we will be able to see. I don't know whether we are able to see something, whether it's inverted or not. Okay. So see, multiple things are written onto this. The first thing is that 45, that is a magnification. 0.65. This is nothing but a numerical aperture. The remaining two things we will talk in the upcoming questions. Okay. So this objective lens is the one which is responsible for uh, for what we can say that the production of the real and inverted image. But one thing we have to understand, that we got the inverted image, but we need to invert it again, right? So that we can see. We don't want to see inverted image in our at the end whenever we see the optical images. So this was my object. It went through the optical objective lens. It got inverted. So it means that we again need to invert it back, right? So that we can see it. And how will we transform from this place to this place? Which lens is the one which are going to transform it back to the real one, like to erect one? Any idea? This we did by the objective lens. What about this? See, in my microscope, there is also an eyepiece. Okay. I think it might be possible we are able to see that the from word which was written, now it again become inverted, right? So this is done by, so the image which was formed by the objective lens, it is again going to get inverted and by the eyepiece. So this is done by the eyepiece. Is it clear? So this thing and this eyepiece and the objective lens, both are going to make the image, whatever their object, like the corresponding object for them, to be the real and inverted. Twice the inversion will get the erect. Okay. Any doubt in this till now? Okay, since there is no doubt, let's move ahead. Let's move to the question number 9. Here is the question number 9. Okay, again it's true and false. So let's hide and do one by one. Yeah, the first one, in microscopy, when the object is placed within the focal length, again we are talking about the last question, the image form is real, is it? Within the focal length. So this is this is lens, this is focal f, this is 2f. So we are keeping somewhere over here. Yeah. Yes, right. Krishna Raj and Rajiv, yeah, perfect. So this is the false. We have done with the question number 1. Let's go ahead. Second option. The magnification of the microscope increases when the object is placed near the focal point. Is it? They're telling that if we are getting more closer toward the focal point, F, yeah, yes, okay, as was as. Okay, yeah, Namrita and Krishraj, that's true. So we will get more magnification if we are moving toward the focal point. Now let's go to the third one. In transmission mode, the image is formed by the light reflected from the surface. In the transmission mode, the image is formed by the light reflected. No, right? It's the transmitted one. So again, it's a false. So the first and the third one is false. Very good. The compound microscope use only one lens to form the image. Will it use only one lens? False, right? The reason we have got that if we use only one lens, we'll get the inverted image. What we want is the erect image. So more than one. It can be two. It can be even more than that. Okay. So with that, it's a false. False, true, false, and again false. Guys, any doubt in this question number 9? Okay, since there is no, we can move ahead to the question number 10. Now in the question number 10, let me tell you that multiple answers can be right. Okay, more than one can be right. How can resolution be improved in the microscope? Now we are talking about the resolution, and we know the formula of the resolution is given by 0.61 lambda divided by mu sin alpha. Mu sin alpha is nothing but a numerical aperture. So Krishnaraj is telling that it's option A. Decreasing the wavelength will improve the microscope. Can be improved the resolution. That's right. Namrata is telling the B. Increasing the wavelength. See, we want to make sure that our resolution should be as high as possible. But if we see from the perspective of the magnitude, R should be as low as possible. Smaller distance we want to resolve. The smaller the distance, more is the resolution. So we want to decrease this. So our wavelength should decrease, and our numerical aperture should increase. So increasing the wavelength is the incorrect answer, right, Amrita? Decreasing the numerical aperture. Yes, Rajiv. It's a option D. So decreasing is not a right one. Increasing numerical aperture is the one. Using smaller aperture. What do you think? We have discussed this in the class. No, we are not using the smaller aperture. We'll use the larger aperture. Larger aperture can gather the more information. Okay, and it can help us to resolve. So the right answer is A, D, and E. Okay, guys. Any doubt in this? Right, aperture should be larger. So okay, using smaller aperture. No. But we encounter more aberration. Suppose resolution is this. Okay, Krishna just wrote something. Let's read it. Suppose resolution is this. 150 nanometer particle may be seen as the bright spot. Can we say that whether it's one particle or these two particles stuck together? Suppose the resolution is this. So the resolution is 250 nanometer, and the 150 nanometer particle may be seen as a bright spot. Can we say whether it's a one particle or it's a two particle? So the particle size, okay, let's say one particle is this, another particle is this, and they are stuck together. So what is the distance between them? The distance between them is 150 nanometer. So we know that. What is the resolution? We cannot resolve anything which is less than the resolution itself. Is there any method to find experimentally Uh, but we encounter more aberration. Is there any method to find experimentally? See, there will be a lot of aberration will be created in this, right? Anyway, it's a very known fact that we cannot resolve something which is smaller than the resolution limit. Okay. For example, a car is coming towards you. It's coming from very far, but at that point you won't be able to resolve that whether it's a car or a bike because both the headlight will merge with each other. So you cannot resolve it. Okay, so because that time your resolution is not that. Once it come closer to you, then only you will be able to resolve. Even if you talk about this thing, no, like okay, the two particles are merged and are we will be able to do or not. So it's not the correct one. We will not be able to resolve this. The point should be this should be a little bit far apart. Okay. Okay. So with that we have solved this question. Right answer is A and D. In higher, so let's Rajiv ask, can we but we encounter more aberration? Yeah, that's true, Rajiv. We'll encounter more aberration as we keep on playing with this numerical aperture part. Okay, yeah. So let's move ahead. Let's go to the question number 11. Okay, where is my plan set? Yeah, here it is. So let's go with the first one. The dash is the closest spacing between the point that can be seen as a subject under the microscope. Krishna Prakash, Krishna Raj, yeah, that's right. So it's a resolution, right? So it's right. Okay, let's move ahead. The product of the refractive index mu and sine alpha, sorry, and sine of semi-angle alpha is called, very good, it's a numerical aperture. Yeah, Na. Now, see, in microscope, dash magnification occur when the further magnification does not reveal new detail. Which type of magnification will occur when we are keep on magnifying the things, but there is no additional image, no additional detail we are able to see. So there is a two type of magnification we know, right? Very good, Rajiv. That's right. It's an empty resolution, empty magnification. So we can see that there are magnification is of two types. One is effective, and another is empty. Effective means that once we keep on increasing and we are able to see the features more clearly, that is known as effective magnification. While if we are seeing something like if we keep on increasing the magnification but we are not able to see any more what we can say that any further information, that is the empty resolution. The right answer is empty. Okay, let me share a few images. Let me show you a few images, optical images which I have gathered. So here we can see that this is at the comparatively, this is the TiO2, rutile TiO2, and we are able to see it in the microscope and the grains are very visible. The reason is that I annealed it at very high temperature. So the grain growth occur too much. Due to that, we are able to see. Now, okay. Now, so if I keep on increasing the magnification, you can see that I'm able to resolve that the particle size more clearly. So this magnification, the increase in the magnification is not the empty magnification. It's the effective magnification, right? So because with the increase in magnification here, we are able to see the resolution also is, we are able to see two distinct particles quite clearly. Here also, okay. So these are the few images which we captured using the optical microscope itself. So this was what is known as the empty magnification. Okay, let's see the last one. The dash effect causes light passing through a small aperture to form a concentric ring at a disk instead of a single spot. What do you think? So which effect it is? Perfect. That's right, diffraction. The diffraction is the one which is responsible for the formation of the array disk. So with that, we have solved this all four questions. If there is any doubt, please let me know. Okay, since there is no, let's move ahead to the next question, question number 12. Okay guys, so now let's solve the question number 12. So what it is that the first question, let's say, resolution and the smallest visible feature are the same. Can we say that? No, right? It's incorrect, it's a false. The smallest visible feature cannot be the same as a resolution. Resolution can be even more for a particular microscope. So this is the false. Let's move ahead. A larger aperture reduce diffraction effect and improve the resolution. What do you think? If we are using the larger aperture, it reduces the diffraction effect and improve the resolution. This is true, right? If we are able to see aperture is more, so we can say that our overall NA, that numerical aperture part, will be more. And we know that if that is going to increase, the denominator is going to increase. So effectively our resolution, the value of the magnitude overall will decrease. So it means that we are able to resolve more clearly. So the option B is the right answer. So it's a true. Right. See, we know that resolution is given by 0.61 lambda divided by Na. Okay, so since this numerical aperture is the one which we are going to we are going to play a lot. In the optical microscope, you can see that, for example, let's say that I showed you one optical this objective lens. See, the first thing is that it's written as 45. 45 is a magnification. 0.65 is nothing but a numerical aperture. So now let's have a look onto one more objective lens, and we'll see that how the numerical aperture is changing over there. Let me remove one more. Yeah. So here we can see that the numerical aperture is 0.4 for the 20x magnification. So which is going to resolve more? The resolution doesn't depend upon the magnification. It depends upon the numerical aperture. So 0.65. This is more. The value is more. It means that the blue one, among this blue and the green one, the blue one is the one having the better resolution compared to the green one. Okay. So it's never the magnification which is the important in the resolution. It's about the numerical aperture over here that is mentioned. Okay. So with that, we have solved the question number B. Let's move ahead. The depth of field and the depth of focus are the same. What do you think, guys? Are both of them the same concept, the depth of field and the depth of focus? So, what is it? What is depth of field and what is depth of focus? Depth of field is a region in which you can focus your specimen without even if you deviate it a little bit, still if you are able to focus, it means that depth of field is good. For example, let's say whenever we have specimen, right, to visualize under the microscope, it will be more or less like this. So some roughness will be there. So it might be possible that our microscope will only be able to focus this region, the top. So if you try to focus this region, these regions will be these features will be hidden. It will not be in the focus. Why? And if you try to focus the below region, the region 2, then the above region will not be in the focus because the depth of field is small. This is the depth of field. Okay. Well, the depth of focus is with respect to the image, where the image is formed. The depth of focus is always higher than the depth of field. So depth of field is related with the object, the specimen, and the focus, depth of focus is related with the image. Oh, where am I? hope it's clear that depth of field and depth of focus, they are the two different concepts. So the answer here is false, right? So we can see that the option C is a false. Now the last one. Electron microscope have the better resolution than the optical microscope due to the shorter wavelength. Is it true? So again, let's have a look onto the resolution formula. That is 0.61 lambda divided by numerical aperture. We'll stick with this formula. Yeah, it's true, Krishna Raja. So it's telling that it's a true because smaller the wavelength, more like the smaller the resolution, like the magnitude of the resolution will be. You can distinguish the more close particles, more spacing. Okay, so that's the reason why electron microscope have the better resolution. Now, if we add TM also here, then in that case we can say that the transmission electron microscopy will have more resolution compared to the scanning electron microscopy, because again the wavelength can be even further decreased, right? So this is clear, I think. So the option D is true. This is true, and the A is false. Right, guys? Any doubt in this question number 12? Okay, since there is no, let's move back to the question number 13. Yep. So for a convergence angle of, that is alpha is given to us, alpha is 7 degree. The refractive index of the immersion is, that is mu is given to us 1.6. The wavelength of the light, lambda is given to us 200. What will be the theoretical resolution and the depth of field in micron? We want to find the resolution and the depth of field. Resolution, we know that it's nothing but R will be given by 0.61 lambda divided by mu sin alpha. We know the lambda. Lambda is given to us in nanometer. See, we know that the numerical aperture don't have any unit. It's a unitless. Lambda is having the unit of the length. So our resolution, the unit of the resolution will be in the length itself. Okay. We just have to convert this to the micron. That's all. Lambda we know, alpha we know, mu we know. We can easily find out what is the resolution. What about the depth of field? Let's talk about the depth of field. Depth of field is given by 0.61 lambda divided by mu sin alpha tan alpha. We know all this thing, right? Lambda, alpha, and mu. Okay, so Krishna Raj is telling that it's 625.9. 625.9. This I hope you are telling in the micrometer, right? So let's quickly do it. Let's quickly do the entire stuff over here. So what you have to do, 0.61 multiplied by lambda, let's say 200 is given to us, mu is 1.6 multiplied by sin alpha, the sine of alpha, that is 7 degree. So it's right. Okay, yeah. So it's incorrect, right? It's in a nanometer. If we want to convert it to the micron, we can write the 0.625 micrometer. Now we just have to divide this again by tan alpha. So we can write that 10 of 7. So the D is given over here to us that it will be 5095.67 nanometer. If you convert to the micrometer, it will be 5.095 micrometer. So this is the depth of field. So the feature, if let us say my feature is quite up and down, in that case we will only be able to, let's say this distance is 5. So we will be able to resolve this to this particular height. Yes, Vita, any doubt?
Yes, sir.
Yeah, okay. So if you can focus particular region, so half of the feature will not be in the focus. So the value, we should always try to absorb this value in the real life. Okay. So this is the reason. This is the reason why we do the polishing at different grade. We make our specimen to be very flat, and then only we can do our stuff. And in SEM, we know that in SEM the depth of field is very high, and that's the reason why you can take a fracture specimen and you can put it under the SEM, and you will be able to see that. So that's how we have solved the question number 13. Any doubt in this question? Okay, since there is no, let's move ahead to the question number 14. In the class, we have discussed about the aberrations. Okay, Krishna Raj has something. There is another formula given for the depth of field to index square of the numerical aperture. Square of the numerical aperture and refractive index times wavelength. So yeah, Krishna Raj is telling that there is another formula for the depth of field, that is mu multiplied by the wavelength divided by square of the numerical aperture. How about you give a try and find the value which you obtained from this? Then if it's working out, then well. Okay, since it's not working out, so let's see the unit. Numerical aperture don't have any unit. This also don't have any unit. So the lambda is the one having the unit. This is correct. Okay, let's try to break it down. D is equals to the 0.61 lambda divided by. Can you tell me what is the answer you are getting? Like how much they are deviated? Because the same formula, like based on the different microscopy, it deviate, but the deviation will not be. It should not be too much. Okay, we'll try to work it out. Let's go ahead to the question number 14 for a time being. Yeah. So we have studied about the aberration in the class. So let's try to solve this multiple match the following question. First one is a chromatic aberration. Chromatic aberration, we know that it arrived due to the presence of the wavelength, the range of wavelength into it, right? So which one is the right answer among A, B, C, D, and E? Corrected using the stigmata caused by the path length difference, wavelength dependent focusing error, right? So the right answer for this one will be the C. What about the second one, spherical aberration? The spherical aberration, it's one of the kind of the monochromatic aberration, right? So when we get to see the spherical aberration, it is due to the, okay, how do we correct the spherical aberration? So guys, A, B, D, or E? Krishna Raj. Okay. For spherical, let's read correct using the stigmata caused by the path difference in the lens geometry. Is it the caused by the path difference in the lens geometry? D. Magnification decrease away from the optical axis. Magnification increase away from the optical axis. See, we know that spherical aberration is occurring due to the lens, the geometry of the lens, right? It's due to the geometry of the lens. So what is happening that the ray which are away from the point, away from the lens, optical axis, will converge at different point compared to the ray which are near to the optical axis. They converge at a different point. This is the one. This difference is the one which is creating the what we can say that the spherical aberration. So the for this right answer is option B. What about the stigmatism? Stigmatism is, we know that this is arriving due to the vertical and the horizontal. The vertical plane are reflected in some other space. Again, the vertical is going to get focused somewhere else. Horizontal planes are going to focus somewhere else. and due to that thing, the astigmatism is right. Okay, so we can use the stigmata to correct it. So the for C, the right answer is option A. 4. The barrel distortion. In barrel distortion, we are aware that the images which are at the center, they will be magnified, and the images which are away from the center, they will be compressed. So the magnification decrease away from the optical axis. Right? So right answer is option B. Cushioning effect is the opposite of this thing. So the right answer here, the option will be the E. That is, the magnification will increase if we are going away from the axis, and it will decrease uh, near to the optical axis. So with that, we have solved this question number 40. If any doubt, please let me know. Okay, for the last answer, the answer got using the formula is this, not the same. Just want to point out. Okay, so the variation is quite large. So we have to check about that particular formula from where it is coming, because in the class we have not seen that. Right? Okay, once our question is over, Q&A is over, then we'll try to work on to that part. Okay, so with that, the question number 14 is over. Let me know if there is any doubt. Okay, since there is no, let's move to the question number 15. What caused the chromatic aberration in the microscope? So what will be the right answer? The chromatic aberration. We have already discussed it in the last question. Okay, so Krishnaraj is telling that is the option B, the variation in the length refractive index with the wavelength. That is right. The refractive index for the blue and for the red one, they are different. And that is the reason that mechanical vibration, no. Incorrect aperture size, no. This is also the chromatic itself means the color, and we can relate that with the wavelength. Okay. Okay, let's move ahead. Let's go to the question number 16. How is spherical aberration corrected in the electron microscope? Again, this also we have discussed in the last question. Let me know if there is what is the right answer of this particular thing. We want to correct the spherical aberration. Reducing the aperture semi-angle. Yes, Rajiv. Yes, Krishna. That is right. So by decreasing the aperture, see, we are talking about the electron microscopy. Okay. By adding the compensating lens system, no, this is not the one. Okay. This we usually do in the optical microscope. For the electron microscopy, we can decrease this thing. See, what we saw in the spherical aberration is that the one which is near to the optical axis, they converge at different location compared to the one which is away from the axis. So by adjusting the aperture, we can remove the image, we can remove the signal which are coming from away from the optical axis. So what we will do is, in that case, we'll cut out that this part. So this we can remove just by adding the aperture. Okay. So with that, we have solved the question number 16. Any doubt in this question, guys? Okay. Since there is no, let's move to the next question. Again, this is related with that aberration part which we have discussed. What is the disk of least confusion? The disk of least confusion in the aberration correction. The point where all the wavelength focus perfectly, a compromised image plane where the blurring is minimized, the edge of the lens where the distortion is least, the focal point of the monochromatic light. Right, so we know that the option B is the right answer. See, we have discussed that they are focusing at two different things. So we can find that there is some location, the region, there will be the disk, the region where we can like compensate this two things, like average out more or less. Okay, so the blurring can be minimized into this vision. So that's why the disk of least confusion is the option B. Let's move ahead to the next question. Yeah. Okay, it's in the inverse way. They are telling about that the what are the things is happening. From that we have to guess. So the what aberration cause horizontal and vertical line to focus at the different plane. What aberration cause horizontal and vertical line to focus at the different plane. Yes, Prithviraj, the option C is the right answer. See, this is happening due to the axis away from the axis near to the axis. This is happening due to the like the plane, the horizontal plane and the vertical plane, vertical line, they are focusing at two different regions. Right? So the option C is the right answer. Barrel distortion, no. Barrel distortion is related with the magnification. Like the at the center near to the focal, near to the optical axis, we'll get the higher magnification. Well, the away from the away from the optical axis, we'll get the magnification lower. Okay. Oh, I not used. Yeah, please answer this. Why do electron microscope achieve higher resolution than optical microscope? We have solved this. We have discussed this multiple times. Exactly same question we have discussed. So why do electron microscope achieve higher resolution than the optical microscope? The answer is the yes. Yes, Rajiv, that's right. The shorter wavelength. That is 0.61 lambda by Na. So decrease the wavelength and we'll get the better the resolution. Okay. Absence of the diffraction effect, no. Higher, let's see that if there is any other options are there. Higher magnification lens, no. Magnification has not to deal with the resolution. Larger numerical aperture, no. In the for the electron microscopy, the numerical aperture, even if you no matter what you change, it will be more or less constant. It's not going to affect much. So the option B is the right answer. Let's go to the question 20. True or false? The monochromatic light emits chromatic. Oh, okay. Let me hide the window. The monochromatic light emits chromatic aberration but not the spherical aberration. What do you think? The monochromatic light will eliminate chromatic aberration but not the spherical aberration. Okay, that's true. For chromatic aberration, there were the like, okay, we say that multiple wavelengths are there, that's a problem. So now monochromatic we use at the single wavelength. So we are able to eliminate the chromatic aberration. But the spherical aberrations, those things are already there. Electron microscope use a refractive lens to correct aberrations. Okay, the electron microscope has a higher resolution, right? So Na will be smaller, right? So for the previous question, option A is also right. Okay. And see, for electron microscope, what we can say that resolution is given by 0.61 lambda divided by Na. Okay. Even though formula is not 100% correct for the electron microscopy and optical microscopy, we cannot say that this is the one which is the responsible, because aberration and all those things need to be accounted. But for a time being, let's stick to this. The mu sin alpha. Now, the resolution for the optical, we know that what we can do, let's say maximum we can go to the 0.2 micrometer for the optical. For the electron microscope, we know that let's talk about the SCM. We know that the result, what we can do is we can go from 0.1 nanometer around. Okay, so how much we are decreasing? Something around 10 to the power of 3 order of magnitude is difference is there. Now let's talk about the optical microscope and A. So mu, let's say we are talking in the air itself, the refractive index is 1. So 1 can be there. So the sin alpha, How much it can vary? Yep. So sin alpha can vary, right? How much it can vary? Sin alpha is very small, okay. So the alpha we can write max to max. It's like alpha is there. We can write to alpha. This is small. That is true, right? So alpha we can decrease it further. So alpha is going to decrease. So again, this thing is going to decrease only, right? Alpha max to max, what we can do, we can make it 1. Okay, someone is showing the alpha is very small. So it's simply alpha in the formula. That is also true. That's correct, yeah. So we can more or less like to be the alpha itself. So the thing is that it cannot vary much. It will vary, let's say 0.65 we have in the optical microscope. See, for a timing, let's see this numerical aperture 0.65. In the optical, we have got 0.65. Maximum, let's say you want to do whatever you can go, it can only go to the maximum value. We want to increase it, right? We want to increase this as much as possible so that we can get the better resolution. Maximum, we can make it to be the 1. Yeah, maximum we can make it to the 1. This thing doesn't take into account the order of magnitude which we are talking about. So the majority, the prime reason, the preliminary reason that for us to get this particular resolution difference between the optical and the electron microscopy is due to the wavelength, right? Because you can see that the order of magnitude that has been we are decreasing, the resolution by which is increasing is more or less related with the wavelength, because we are also decreasing the wavelength of the electron in that to 3 to 4 order of magnitude. So in the like 0.5 Angstrom, you can say something like this. So yeah, okay, that's clear, I think. 19th, yeah, so we were over here. Electron microscope use a refractive index to correct the aberration. Is it? Sorry, refractive lens. Electron microscope use refractive lens to correct the aberration. We know that it's a false, right? It uses the condenser lens and all those things, like we can increase the, let's say some aberration is there in the astigmatism, let's talk about that. So we know that one axis, the power of the one axis, like it's focusing somewhere else, and the vertical is focusing somewhere else, horizontal is focusing somewhere else. So you can change the field, you can change the strength of the field and converge the electron in such a way that now they are going to coincide. The vertical and the horizontal should coincide with each other, the point where they are focusing. So it's not these things. In electron microscopy, we don't talk about these things. Okay, refractive lenses and all. This is in the optical microscope. The barrier distortion occurs when the magnification increase toward the image edge. Is it? Barrier distortion occurs when the magnification increase toward the image edge. No, right? Very good, Chris Prasad. So it's a false. So we can say that this is a false. It's the other way around. Like the magnification should be more towards the center. Okay, and toward the edge it should be less. Now this last one, the theoretical resolution of electron microscopy is limited by the atomic size. What do you think? The theoretical resolution of the electron microscopy is limited by the atomic size. False. Then what is the correct answer? So what it is that is limiting this resolution in the electron microscopy? Diffraction. Diffraction is one of the reason. What else? We can we say that the, yep, yes. So again we came to the central maximum. Okay, so see, whatever we have obtained using the central maximum, also the array disk, the size of the array disk we made it too small. Okay, so compared to that we could have got fall in the second central maximum fall in the second minimum. Yeah, that's true. That is a condition for the Rayleigh criteria. Okay, the Rayleigh criteria, what you are talking about is perfectly right. That we take this particular two wave, the maximum of one should lie over here. It should be something like this, right? This is what you are saying. So with that, we should have got around zero point 0.2 Armstrong because the array disk is quite small. So the what is limiting is the aberrations. Instead of 0.2, we are getting some few order less. Spherical aberration exists, maybe that. Yes, perfectly right, Krishnaraj. So it's due to the aberration. So with that, we have solved this question. Screen is not visible. Uh, is it fine, guys? Now, pardon me for that. I'm not much. Okay, that's good. I'm
Now
not
it's
much.
visible.
Okay, thanks, Namrata. So the here we can say the answer is false. See, I'm not good in that screen. Like I have that writing pad for the screen, which we can write in the PPT itself, but I prefer the pen and paper. So with that, we have solved this question number 20. If there is any doubt in this, please let me know. If not, let's move ahead. Yeah, so now we are coming to the good questions. In optical microscope, what create the image contrast? Only the direct beam, interference between the direct light and the diffracted light, magnification power of the lens, background illumination intensity. Rajiv is telling that is the background illumination intensity. Okay. Yeah, this is also the right answer. Is there anything else, Rajiv? Will there be anything else? See, the interference between the direct light and the diffracted light. This is the prime answer. Okay, yes, that's good. Option B is the right answer, Rajiv. So it's the interference. We know the interference. What is happening that the few things will be like the white and black spot will be created. The diffraction will occur, and due to that, I think we are able to see the contrast. For example, the green and the green boundary they will give the different contrast due to the scattering. Now, what is happening at that point is the diffraction. It's going to some other direction. So the interference between the direct light and the diffracted light is the one which is creating that image contrast, and also this is also there. Now the contrast due to this we want to minimize it, like because if background intensity is too much now, we won't be able to get the good signal to noise ratio. So signal to noise ratio should be there, something around 5% it should be. Then only it's the signal considered to be the good. Okay, so with that we have solved the question number 21. If any doubt, please let me know. Yeah, question number 22. What is observed in the back focal plane of the objective lens when using the diffraction grating? What is observed in the back focal plane of the objective lens when using the diffraction grating? Okay, a magnified image of the specimen, a central spot, and the diffraction spot, only the darkness, a reflection of the light source. Only the darkness? No. Magnified image of the specimen? No. What we are able to see is the central spots are there. Okay, and then there is a diffracted spot. We saw that at the center there will be the intensity will be very high, and after that few spots are will be there, right? The bright and the dark spots will be there. So if we use the diffraction grating, then only then we are going to get this particular part, the option B. Let me tell you one thing: the optical image which I showed you on in the lab, which is present to me, there is no diffraction grating attached to that. What is the use of the diffraction grating and under what condition, which optical microscope should be used? This thing we are going to cover in the upcoming week 2. A detailed lecture is there onto this. So, but if your aim is just to see your image, the normal optical image which you are seeing, that then that particular optical microscope doesn't need the diffraction gate. Okay. So with that, option B is the right answer. Any doubt, guys? Please let me know. Okay. Yeah. So this question, professor has discussed about this. Like according to the ABS criteria, what is the minimum requirement for the image formation? Something which Rajiv has told us. Only the zeroth order beam and at least one diffraction beam. Yes, and two diffraction beam without the direct beam. Only the first order diffraction beam. So the rest, yeah, it's correct. The right answer is option B. Right. So we know. Wait a minute. Okay, the question is right. So this is a criteria that zeroth order beam, like the transmitted beam should be there and at least one diffracted beam should be there. Okay. So this is the criteria for the formation of the image. Okay. Yes, Rajesh, please. Is it good to have more diffraction in the electron? Uh, See, the diffraction will happen. The diffraction will definitely happen, and that is the reason why we are getting the error disk. You cannot avoid that. This is the nature of the wave. Okay, in that is the reason that why we are getting the spot size is larger than the beam size, right? So the diffraction you cannot avoid. Is it good to have a more diffraction in the electron microscopy? Without diffraction, the imaging will not be possible, right? It is due to the diffraction only we are able to see the images. The reciprocal lattice, the diffraction pattern which we get. See, for example, let me tell you. If there is a screen and there is a beam which is coming to it, and there are the other beams, diffracted beam. So there are the MP of information is also is saturated in this particular diffracted beam. So sometimes what we do is we don't focus on this beam, the transmitted one or the bright field one, the center one. We focus on these things. This is what we sometimes like focusing, like the you can move your photosensitive screen from here to here and you can see that okay, the pattern from white it turned to the black. So for example, in the upcoming week we are going to discuss about the ACI, electron channel contrast imaging, in which this diffracted beam is used in the very large extent. Okay, so without diffraction the microscopy is not possible, right? So this is what the answer I can give you right now, but the answer will keep on evolving as we proceed further to the upcoming weeks. I hope I am clear. If not, please let me know what doubt you have further. Okay, so if there is any doubt, let me know. If not, we'll move ahead to the question number 25. So more diffraction. See, lights are the wave, electrons are the wave, and diffraction will occur. Without diffraction, you cannot see the images, right? You cannot, we cannot visualize it. So diffraction is the one, yeah. So more diffraction is good. Because the diffraction is carrying a lot of information. Okay, so now let's go ahead to the question number 24. Okay, Krishna has told that the option B is the right answer. Let's first read the question. What is the primary function of the condenser lens? So what is the primary function of the condenser lens system in an optical microscope? To magnify the image, to organize and guide the light ray through the instrument. Okay, yeah, that's right, Rajiv. The answer is option B. So what condenser lens is doing from the word itself, it's condensing the ray of the our optical light emitted the ray. Now, this lens, the condenser lens, can condense them to one particular point, and now this will act as a source. Okay, so to organize and guide the light through the instrument. So this is the part of the condenser lens. This light is the one which is going to interact with our specimen, and after the specimen, it will come to the objective lens where we are going to see the image and all. Right. So the option B is the right answer. Let's move ahead. If there is, yeah, sorry. If there is any doubt, please let me know in this thing. Okay. Since there is no, let's move to the question number 25. Which component of an optical microscope is responsible for the primary image formation? What do you think, guys? This is the most important question we can say. Yeah, that's right, Krishna Prasad. Krishna, yeah, that option C is the right answer. The which component of the optical microscope is responsible for the primary image formation, that is the objective lens. Sample stage, no. Condenser lens, no. Condenser lens is only going to condense the, it's going to make the virtual light source. Okay. Eyepiece, no. Eyepiece is also going to participate in this, but the primary one, the main, the factor is the objective lens. The optical microscope which I showed you, it has only the maximum of 45x. Okay, so the objective lens is 45. It can go to the maximum magnification of 45. So multiplied by 10, it will be 450. If we increase it, if I want that, okay, it should go to the 100 also. 100x should also be there, which will respond, which will reflect it to the 1000x. Then the price of this thing will increase by 2 lakhs, 2 to 3 lakhs, it will increase. Okay. Okay, so with that, we have solved this question. Let's move to the question number 26. So we are left with the only 3 to 4 questions now. Now, what is the advantage of using coilers illumination in microscope? Coilers illumination, it means that what we are adding one more thing over here, right? We are adding one more lens. Can anyone tell me which lens is it? Yes, that's right, Chris Raj. Just a minute, guys. Yeah. So it's going to add the collector lens. So it minimizes the scattering and provide the better brightness control. Yeah, the the working of the collector lens is to control the scattering, the light which is coming from the source. Okay, so it will to minimize the scattering and provide the better brightness control. Okay, so most of the microscope, let me tell you, like when we add this particular collector lens, the microscope cost will be very high. The present microscope which I showed you, it doesn't has that this particular thing, the collector lens. It only consists of the condenser lens, and then after that we have the objective lens, and then the eyepiece. So that was the thing. So, but in our department we have this particular coiler illumination microscopy also, with and I use this particular one when I want better resolution. But for the crude way, just to do the research sometime, like I can use this particular, the present one which I am having. But to report in the scientific community, I usually use this particular microscope because it provides one more handle to control the brightness. So that was the one. 26 is over. Any doubt, let me know. Let's move to the question number 27. Yeah, this question. Why are the inverted microscope commonly used in the biological research? What do you think? Why are the inverted microscope commonly used in the biological research? Option B, they provide the easier focus of the specimen in the aqueous medium. Is it? Mm, they provide the higher magnification in the upright microscope. They are the cheap. They don't. Yes, option B is the right answer. See, the reason is that those biological those component that cells and all in the aqueous medium once they are there, they tend to settle. So let's say this is my beaker, contain the liquid, and it is also consisting of the few biological particles, some cells. Now after a time, what happened that they tend to saturate to the bottom. So you cannot visualize it. We cannot visualize that if we are using from the top, if we are not using the inverted one, we are using the upright one. In that case, yeah, yes, that's right. That's right. It's due to the gravity. But due to the gravity, it's tend to saturate, and we won't be able to visualize it. While that's the reason why if we use the inverted one, if we are going to analyze it from the below, then we are able to see these particular cells. One more reason I can give you that sometimes what people bring that in my life, usually few people bring that their size of the specimen will be quite high. The height will be high, which we won't be able to put in the upright microscope. If we are trying to put the optical lens, the objective lens will sometime collide with the specimen due to the more height. So in that case, what is better? It's better to keep it onto the inverted. So nowadays, I would tell you that most of the microscope that are present, which people are trained to buy, it's only inverted. So in my department, we have 3 optical microscope, and all 3 are the inverted. Okay, so with that, we have solved this question number 27. If there is any doubt, please let me know. If not, let's move to the question number 28. This is the last question. Okay. True or false? The first one. The specimen stays in an optical microscope only move horizontally. It's very childish type of question, I would say. It's a false. It has to move in the vertical direction so that we can focus it. The focusing is majorly, see, the position of the objective lens is fixed. So what we can do is we can only play with the stage. We can change the location of the specimen and brought it to the focus. Second one, the higher magnification. Rajiv, you still have doubt? Like I see your hand raised. Oh, pardon me. Higher magnification objective lens are typically shorter in the length than the lower magnification one. Higher magnification objective lens are typically shorter in the length than the lower magnification one. Rajiv is telling it's a false. See, I showed you that this is 45 magnification, right? And I think I might have shown one more. No, then where is another lens meant? Okay. I'll search it later on. For a timing, let me remove another one. And this one is having the magnification of 10. Okay, 10 is written. So now we can see the height. So the higher magnification objective lens are typically shorter in the length than the lower magnification one. Yes, it's a false. That's right, Rajiv. So the answer is false. It's the other way around. Higher magnification lens are typically shorter in the length than the lower magnification. Yeah, it's false. So now let's go to the third one. The Coiler illumination used a collector lens to collect the virtual light source. What do you think? True. Right. So with that, we have solved the question number 3. So if we see the optics, like how the things are placed, first comes our source, then the collector lens, after that condenser lens, then it will go to the specimen, then from specimen it will go to the objective lens, from objective lens it will go to the eyepiece. So if we write it down entirely, so from the source the light is coming, from here it will go to the collector lens, from there it will go to the condenser lens. Let me tell you, like all the lenses, they come with the aperture also, so it will always be there. Condenser lens, then it will go to the specimen, then it will go to the objective lens, then from there it will go to the eyepiece, then the human eye. So this is the entire the optics, how it is happening, the pathway, how the things are there. So yeah, now let's move to the question number 4. The inverted microscope are perfect for the metrography due to their design simplicity. It's true, right? I just told you that we can simply put even the smaller or the larger specimen on top of that. The numerical aperture of the condenser lens affect the resolution of the microscope. The numerical aperture of the condenser lens. Yes, numerical aperture of the condenser lens is going to affect the, because that is one which is going to see, okay, how much light is coming. The numerical aperture, the entire significance is that how much light is it can capture, it will take, how much opening it have. Okay, so the numerical aperture of the condenser lens affect the resolution of the microscope, that is true. So with that we have solved this 28 questions. If there is any doubt in this, please let me know. And if any doubt in the lecture that has been discussed till now, that 5 lectures which we went through, if there is any doubt in that, please let me know. If not, let's move to the question of what Krishna Raj told us. So for the time being, how about we try to find, for this particular lens, the numerical aperture is given to us. Can we find the resolution of it? Please work it out. Meanwhile, once I will search that question first. So we know that 0.61 lambda divided by Na. For this particular lens, how much Na is given is 0.65. And Na is given lambda we know that visual light is 400 to 700. So how about we take something average in between them, that will be around 550 nanometer. Let's take our wavelength to be the 550 nanometer. We have to find the resolution. Yeah, so that equation was for the electron microscopy eyepiece, where the sin alpha is equal to the tan alpha. Okay, then I'll go through that. I'll try to search what it is, and I will let you know in the next class. Since it is the electron microscopy, I think it might be there in this Joseph Goldstein book. So I might have to went through few chapter of it. Yeah, it's a very good book which is recommended by our professor. You can see in the first slide itself, he told that this is something which we can refer for the scanning electron microscope. Okay, so we'll try to work on to that, and I will let you know, Krishna Raj, in the next class also, like from where that particular equation. I forgot the equation, what it was. Okay, I will have a look on to the chat box. The equation which you told that whether it's correct or not, first that itself is a doubt. Depth of field. I just said it's for the depth of field, not for the depth of focus, because depth of focus is mostly higher and the value which you are getting is also very high. Okay, we'll have a look. Mu lambda divided by numerical aperture square. Okay guys, I will do one thing right now. I will just show you the couple of all the questions that we have discussed till now. Just have a look onto them, and again, I'm telling you, if you find any doubt in any of this question, let me know. Here we talk about the inverted microscopy. In the covalent illumination, we have talked whether that we can add the collector lens and increase the resolution. Then what is the primary function of the optical objective lens that we have discussed? This about the condenser lens we have discussed, about the Abbes criteria we discussed, and then we discuss about that grating. Okay, diffraction grating, when to use. Again, the diffraction grating part is going to come in the next week, so we'll discuss that thing in more detail in the upcoming dot solving session. This is a question 21 where we discuss about the image contrast, which can arrive from the diffraction as well as from the, what we can say, the background and the image. Then there is, we talk about the resolution of the electron microscopy. There is a lot of questions we talk about the resolution of the electron microscopy. Now the couple of questions based on the equation we have discussed. Disk of disk confusion. How to correct them, that is also few questions we have discussed about them. This is this question more or less summarize that what is, which aberration is there, what they are responsible to.